Hey everyone, welcome back to my channel EduVibe. Today we will start with another topic of forces and fields. As you all know, we're doing the magnetism, and today's topic is moving charges in the magnetic fields. So we are discussing the magnetic fields in the previous videos. Now, when the charge is moving in the magnetic field, so what will happen? So from here we will get into the left hand rule number 3, which is the 3a because we do the 3b. Both are the same, but both are used in the separate lessons. Like 3a is the rule we use now, which involve in the magnetic force now. So this we have to discuss. We discuss about the one equation to two equations, and that's a very important equations of that magnetism part. Let's start with this. First, we have to know what is magnetic force. So the charged particle undergoing the uniform motion, when any charged particle undergoing uniform motion, which is a straight line motion, and will produce a circular magnetic field around it. So you can see when anything goes into the uniform and this goes like uh, in the magnetic field, this is the magnetic field into the page, and this will get the circular part of like motion like this. So this is circular type of motion you get, and here some angles are making like this. So these angles are discussing the circular part, and the angles are used when we making the circular motion equation, which is not on the data sheet. We later on discussing about this in this lesson too. So intersection of the induced magnetic field of the charges, which is a circular field, this is now called a circular field. It is all called the circular field because in circular we get the magnetic field. And an stellar magnetic field produces the magnetic force. From here, in this one, our magnetic force can be introduced. That this is the magnetic force of the specific, like circular part of this. So when we do the uniform motion of the charged particle moving into the magnetic field, and we get a circular motion, from here the magnetic force can be generated, can be made in that case. So the force can be involved in that case. Acts on a charged particle which causes deflection of a straight line. You can see the deflections over there. This is a deflection. These are the deflections of the any, and you have any charged particle. So that's why we're doing the hand rule, a left hand rule again, to get that where the magnetic force is, where the magnetic field is, and where that velocity goes, where is the particle going, where is the particle moving, in the which direction they're going. So that's all we can discuss with that left hand rule, number 3a. So that's the rule we have. So this is number 3a rule. So we have to be like in this type of hand movement of the left, or we have been in, I think we not have in this, but in the different I like something with the left hand we do thing like you do like your one finger over there and the point is over there, one goes over, one goes like this. Something like this the type of can we I made with our hand to get know about that what the direction is which. So with the hand movements too. So to determine the direction of the magnetic force, what is causing deflection actually, and on charge by the external magnetic field, form a step setup of the third left hand rule we can apply in that case. So point your thumb in the direction of the charge movement. So this thumb is doing the direction of your charge movement, where the charge goes, where the charge movement is happening. Pointing your fingers in the direction of the external magnetic field. This is calling the external magnetic field. We go to by B vector, and this is shows the external magnetic field in your whole mechanism. The direction your open palm. This is open palm, and this direction will shows your magnetic force. So this will be your magnetic force in that case. In that case, your thumb will shows the velocity, your index fingers shows your magnetic field, and your middle finger shows your magnetic force. So these three things have been made with when we made this type of thing. With this is that. So the velocity of the particle, the external magnetic field, and the magnetic force are all mutually perpendicular to each other. You can see in this too, in this diagram too, you can see that all our things are the mutually perpendicular. This perpendicular this perpendicular this. In this too, that all are perpendicular to the each other. That shows that these are eventually perpendicular. So, that's the this thing you have to be mindful in this. For the next one, so magnetic force is more likely the circular motion. So both are going hand in hand, and one formula and one equation you can generate it from that. So what is that? In grade 11, that an object undergoing circular motion, which is also known as the centripetal force. You can know this from the grade 11 that the object which is going to circular motion is called the centripetal force. So that's how centripetal motion. Due to an external force for an object to deviate from a linear path to a circular path. They go from a linear path, like a uniform motion, to the circular path like this. So the sum of these forces referred to as a centripetal force, and from here you can generate one equation like this one, which is centripetal force is equal to mv square upon r. So this equation is not on your data sheet. You have to memorize this equation, and this shows some values like v shows your tangent circular path like this, which is the velocity. EC, which is your acceleration type thing, and directed towards the center of the circular path. Tying of the radius, you can say, not the acceleration. This is the AC tying of the center of the radius. And the FC is directed towards the center of the circular path, and this is your centripetal force. From here, you can also see your mass. So this geometrical formula Fc is equal to mv square upon r, and magnetic force provides a centripetal force. So if you kind of any question where you involve the force and the circular motion, so you can use that thing that Fc is equal to Fm, which is a magnetic force is equal to centripetal force. When we do this, you can write this formula. You can write the magnetic force formula, which we discuss now in later on the next slide. So that's the thing you can use when you do equations and type of forces when you do calculations in that type of thing. So now it's that thing. Calculate the magnetic force. So for the magnetic force, this formula is on your formula sheet, data sheet. You have that formula, so you need to memorize, but this have to memorize. So this is Fm is equal to QVB. So from here, Fm is your magnetic force, magnetic force in newtons. Q is your charge of the particle in coulombs. V is your velocity in meter per second, and then B is your vector. As you all know that this is a magnetic field strength in capital T, which is Tesla. So that's the two formulas you have to know. Data sheet, not on data sheet. This is on data sheet. So that's the thing you have to do. So we have one example over there for that equation to be used. How can we use that? So we have to deal with that. So negative chloride ion we have over there. We have negative chloride ion of charge of this and the mass of this. Traveling at 8.0 10 per 3 meter per second, enters a magnetic field at strength of this 0.0355 Tesla. As shown below, we have to determine the direction of the magnetic force experienced by the chloride ion when it first enters the field. So this is the type of the field we have, north and south magnets we have, that the type of the field we have over there. So what type of field they have, and we have to find the magnetic force direction first. Then we have to find the radius of this. So firstly deal with the A part. So for the A part, what direction they have? So as you see on this table that force goes in that direction. This is the direction of the force. That's the direction of the velocity. So your velocity goes like this. If velocity goes like this, your magnetic field will make something like in this. The magnetic field will like generated over there, and the magnetic field strength goes like this, goes over that direction. And if this goes like this and this goes like this, so where's your the magnetic force goes? So it goes like this. When you do the hand rule, you can see it goes out of the page. So not into the page, it goes out of the page. So Fm out of the page. You can show this by that cross sign if you want. So is out of the page in that case. So that's the thing. And if you want that magnetic field was they're going in like kind of a circular motion. They go in the kind of circular motion, and something at radius you have to find in that case. So that radius you have to find, and you can see that Fc and Fm is both going over there. Centripetal force and the magnetic force both are in this. So this means you have Fc is equal to Fm. So Fc is equal to mv square upon r, and Fm is equal to qvb. That v square with 1v cancel out. You want that r, so you get mv upon q times magnetic field. So I want to solve over there. So r is equal to, so you want mass, so you have mass over there, which is 5.88 into 10 raised to power minus 26 kgs. Your velocity is also there, which is this. So this is 8.00 into 10 raised to power 3 meter per second. Your charge is also given to you, which is this. This is elementary charge, 1.6 into 10 raised to power minus 19 coulombs. And your magnetic field is also given to us, this one, 0.0355 Tesla. So when you do a multiplication and when you do the dividing, you get about 0.0828. You want 3 digits. So that's the answer. That's the radius we have to find in B part. So this has find it. So you can find this. Very. So that's how you can deal with that equation, that relationship between circular force or the tangible force and the magnetic force. So that's all thing you do, and that's the end of this lesson. So we discussed about that, all the thing about the circular motion and the force. So you can now introduce with the magnetic force too. In the next lesson, we discuss that all the concepts, and we discuss in some others when we do in this lattice fields when we do. So the concepts can be related to that topic when we do next time, which is the crossed fields. Like we do the straight line fields. Now we do crossed fields when we have like other type of thing we get in the context of the all the context of the magnetic force in the magnetism part. So learning by simple EduVibe, learn smarter but not harder. Please like, share, and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till then, stay connected with EduVibe.